Hello and welcome back to another episode of Math with Zone. Today we are going to be doing conservation of angular momentum. Okay, so angular momentum is defined as this L, and it is equal to the I times the omega, all right? Which is essentially its inertia times its velocity, okay, the angular velocity, all right? Now there's another symbol as well, which is sometimes called a J, but more importantly, I call it the angular impulse, which would be equal to the torque times time. And you could also think of the angular impulse as the change in momentum. Okay, so angular impulse is equal to the change in momentum. Now you have a whole bunch of different formulas that you can manipulate. And just as a refresher, momentum, in case you didn't know it, is how difficult it is for something to actually stop spinning. All right? So, with that in mind, notice how it says change in angular momentum here. You could, because it says change in angular momentum, think of this as I omega initial minus I omega final, and typically, I guess it goes final minus initial would be more accurate, would equal to the delta L as well, the change in angular momentum. All right, so let's do a few problems here. We got a, I guess I'm doing this one. And I got the answer key right here, so I'm going to kind of cover it up and go side by side. So a uniform 3-kilogram rod that is 2 meters long, free to rotate about its center by the hammer of Thor. The rod is struck by a 1,500 Newton force for 8 seconds directly perpendicular to the rod. What is the angular velocity of the rod after impact? Remember, for these problems, you're going to be given the I equation because it's different for each and every object. There's some that you'll end up memorizing, but for most of them, you won't. All right. So because it's pivoting at the center, it's 1/12 ml squared. You can also see the L as like the length or the radius of the circular thing that's spinning. Our angular impulse is going to be equal to the change in L. And as I told you before, just a second ago, that would be the final minus the initial velocities and their momentums. And there we have our formula. Now remember that change in L is equal to torque times time. That's what we have here. We have torque times time is equal to the final velocity minus the initial velocity, those angular momentum equations. Now it started at rest. It says somewhere. Struck at there. It was starting at rest before Thor's hammer smashed into it. So that's going to equal 0. So we really have torque times time is equal to the inertia times the final velocity. And we also can replace the torque formula for torque is equal to the force times the length times time. Now the length is L over 2, okay? So the length is L over 2. We still have 1/12 ml, and then we are replacing a squared here. ml, oh, it was ml squared delta f, or not, omega f. And then the squareds is eventually going to cancel. There's canceling out the L, canceling out the squared. All right, see what we did here on the answer key. So from here, what can we do? Well, what are we actually looking for? We're looking for the angular velocity of the rod after impact. So if we're looking for this omega f, this angular velocity, we're going to probably multiply by 12, divide by mass, and then divide by another L. So let's see what we did here. We multiplied by 12, that's how that ended up on top. 2 would be on the bottom. We divided by mass, that's why it's on the bottom. We divided by L, that's why it's on the bottom. And if we calculate this, negative 12 times the force, which was 1,500, if we plug in that, if we plug in the 0.08, if we plug in the mass, and we do all the calculations, you get negative 120 radians per second, which is why it is going downward. All right, we got another idea of angular momentum is going to be conserved, which momentum will have to be the same. And if the initial momentum and the final momentum have to be the same, then we can do a few neat things with it. So, a very famous and typical problem that you'll see here is whenever you have a bullet or some sort of trajectory running into a door or some sort of hinged system. All right, so we have a bullet with a mass of 0.2 kilograms is shot at a 40 kilogram door at its unhinged end. So essentially, we have a door, and then we have a projectile hitting said door. All right, after it hits the door, it's going to be hinged over here. That door is going to kind of swing a little bit, assuming the bullet gets wedged into the door as well. So this actually incorporates two things. You got the weight of the door and you have the weight of the bullet, and both of which are going to have their own angular momentums and before and afters. But according to the conservation of angular momentum, they must be the same afterwards. So first, the speed of the bullet is 200 meters per second, traveling perpendicular to the plane. That's very useful. The bullet becomes embedded, making it a perfectly inelastic collision at 2.5 meters high and a 1.5 meter wide door. The 2.5 meters high doesn't matter because the length of this door, or the width of it, so to speak, being 1.5, that would be the L required for right here. All right? And there are two things that we will have to recognize. The first is that the door inertia is provided. That is the 1/3 mr squared. The other thing that you have to know is that if this bullet is going to be embedded on the edge, it is going to be mass radius squared. Okay, so that's going to also be in there. But those are going to be provided for the majority of things. All right, with that in mind, flip some things around here. The angular momentum initial must equal the angular momentum final. What is the initial? Well, the initial is the bullet and what the bullet is doing. Well, the bullet has a mass times velocity, its velocity, times the radius because it is going to be hitting the door probably at the end. I think it tells us where it hits. It is embedded, which is, we're assuming it's going to hit at the very, very edge, okay? That would have to equal the final. Well, the final will be the eye of the door and the bullet, because it is being embedded, times the angular velocity. Okay, which is what we are looking for. So, mass of the bullet, 0.2 kilograms, times its velocity, 200 meters per second, times the radius, 1.5 meters wide, will equal the mass of the door. Do we know the mass of the door? A 40 kilogram door. Times its, the eye of the door. Well, the eye of the door would be 1/3 mass L squared. So that would be 1/3 its mass times 40 times the L, which is 1.5 squared, plus the eye of the bullet. Well, the bullet's inertia is going to be, see if I can find it for you again, a mass at the end of it, which is going to be mr squared. So if we have that, that would be just the mass of the bullet times the radius squared. All of that is going to be multiplied by our angular velocity, so that would be right here. If we're solving for angular velocity, we would take the 0.2 times the 200 times the 1.5, and then we would be dividing by all of this stuff. So if we divide by all of that stuff, the 1/3 times the 40 times the 1.5 squared, and then plus the 0.2 times the 1.5 squared. If we do that, you get your angular velocity, and your angular velocity after doing that calculation is, drum roll, let's see if I can find it, 1.97 radians per second for that angular velocity. Okay, and then the last question before we leave would be, how would the answer change if the bullet is hitting closer to the door? Well, let's think about what would happen here. What do we have on the top? We have the radius of the door here, the 1.5. One time. So if that got closer, this would get smaller. And if these got smaller, what would we end up doing? We would end up dividing by a smaller number. Well, what would happen if we divide by a smaller number? Well, if you divide by a smaller number, there will be more angular velocity. So the angular velocity would increase, according to my logic there. All right, that's going to do it for me today. Until next time, everybody, stay positive, and I will see everybody later. Bye.